I'll
Okay,
introduce you, Josh. Don't worry.
Yeah.
Welcome everyone. Welcome to our 152nd Reading Online Sports Economics Seminar. You say good morning, good afternoon, whatever. We're very thankful that today Josh Miller has stayed up until 1:30 a.m. local time for him, where it's already Saturday morning, to present. Title is on the screen. Surprised by the hot hand fallacy, 5 years on, contributions, criticisms and new directions. Before letting Josh take over, I'm not going to take too long given it's late already for him. Just to say that as mentioned last week, we are now generously and kindly sponsored in the Roses series by the Sports Economics Review, which is a new journal in the field of sports economics. You may not be able to see on my background, but I do have the front cover. But Google Sports Economics Review if you're not familiar with the journal. The journal is generously supporting us in the series. And it is also generously sponsoring the third Reading Football Economics Conference in May, which is joint with the Sports Economics Sports Management Annual International Conference. So please do consider attending that amongst other conferences that are taking place in person this summer. One quick one just to note is that the German Sports Economics Conference, AKIASE Conference at the University of Bayreuth in Germany, that has a submission deadline of January the 31st. So that's a note to me as much as anything to make sure I get something submitted. But if you do fancy a trip to Germany in the summer, then do look out for that. I'll put details of conferences in the chat. There's stuff in the reminder I sent earlier on. I don't want to stop Josh any longer. He's happy to take questions as he goes along. So if you have questions, do raise your hand and I'll interrupt Josh, or just interrupt him yourself if you want to. And without any further ado, Josh, please do take away your talk on the hot hand fallacy.
Cool. Thank you for having me. Thank you, James, for the intro. So please do interrupt me if you have questions. I'm unable to see everyone once I get going because the menu kind of goes behind. So I'll just get going. So quickly, just an overview of what I'm going to be covering today. So I'm going to begin with just a kind of a brief background in the hot hand fallacy. I think most people are familiar with what it is, but it's good to have kind of get everyone on the same page. Then I'll spend a little time on this surprise paper, which is a paper that's been published, but I think it's a good kind of setup for the rest. Then a more recent paper, this cold shower paper, 20 minutes. That paper is coming out, I think, by the end of this year. Then the 3-point contest paper, and then some review of some recent papers on it. We won't have time to get to the betting and prediction paper. So quickly, what's the hot hand? So the hot hand kind of generally refers to this idea that players, or not just players, managers, any type of human, can get a temporary boost in their ability or talent or their probability of success. So a question that's naturally asked in the context of expert practitioners who are motivated to do well, etc., like investors, managers, and athletes, are they going to be operating at peak ability? And if they are, we should expect them to behave consistently. So the question is, do experts exhibit the hot hand? And if so, can they detect it or react appropriately? And so the received wisdom, say circa 2015, was the answer to the first question is no. And so therefore the answer to the second question is clearly no. So kind of the general motivation why economists might care about this stuff is economists care about sequential data. You might care about coin flips, stock price, weather, search decisions, things like this. And there's a fundamental misconception of randomness in settings like the ones you see above, which is this idea that the lay definition of random is that something doesn't have a pattern, but the formal definition is that there's an IID process, and we have this formal definition that we have. And so the layperson thinks, well, there can't be a pattern, but if there can't be a pattern, you're automatically going to violate the formal definition, because to not have a pattern becomes predictable. So for example, if 4 heads in a row is a pattern and you have 3 flips and you can't have patterns, then predictably you're not going to get the fourth flip. And so things become predictable, or things are more likely you're not going to get the fourth flip being heads. And so this predictability, which comes along with the pattern thing, is a common misconception. So people tend to treat streak patterns as informative when they're not. And the things we're familiar with here are gambler's fallacy and luck. And so the challenge circa 1985, and I'm kind of setting up for this original hot hand paper that Gilovich, Vallone, and Tversky wrote, is they wanted to find a tractable field environment in which people have incentive to have correct beliefs, but do not. And so they have this canonical study where they think the sequences of makes and misses in basketball offer an interesting context to test this outside the lab. Why basketball? It's relatively simple. I mean, you'll see that it's a little more complicated than that, but I think you guys know this. There's abundant sequential data. Of course, this is in the 1980s. We have lots bigger data sets in other settings now. Professional decision makers, strong incentives, and people believe that streaks signal a hot hand. So they had this conjecture that these seeing patterns in randomness that you would see in other studies would carry over into this field environment where you have professionals that have incentives. So they'd be making mistakes as well. And so this is the classic thing. Did someone just jump in with a question? Okay, someone's microphone is on. That's fine. Okay, so this is the original paper. I just want to give you a quick kind of view of what is in that paper. So first they survey beliefs, and they find that everyone believes in the hot hand, basically, and that's kind of there. Then they analyze different types of basketball shooting and incentivize betting. And so what are their findings? They find that the probability, or their estimate of the probability of success given recent success, is approximately equal to the probability of success given recent failure. And so a streak of failure doesn't predict any differently than a streak of success. And in addition, players and observers cannot predict any better than chance when they're trying to predict somebody's basketball shot. So players betting on their own shots and someone observing. And so the conclusion is that they accepted the null hypothesis. Basketball shooting is statistically indistinguishable from coin flips, and the hot hand is a cognitive illusion. So the belief itself is a fallacy. So there's the reaction that we have to this, and it was a big reaction because it was a bias that's robust to explanation, and that's a bit unusual. So practitioners stubbornly refuse to accept the results. So you have these famous quotes. Here's Bobby Knight saying there's so many variables involved in the shooting of basketball that a paper like this doesn't really mean anything. Here's Red Auerbach saying, so he makes a study, I couldn't care less. And there was a reaction to the stubbornness. So here's Tversky commenting on the stubbornness. He said, I've been in 1,000 arguments over this topic, won them all, but convinced no one. And so the consensus 2011 is that the sequences of success in this shot satisfy all tests of randomness. The hot hand's a massive and widespread cognitive illusion. And there was a meta-analysis that looked at a bunch of studies and said there's really no point in investigating this any further. Okay, so it was cited a bunch in finance, wagering markets, lotteries. I haven't updated these sites for a while, so there's been obviously more sites since 2016. And so in 2018, this is a paper that I published along with Adam Sanjurjo, who's at University of Alicante. So in your time zone, which maybe we should have arranged for that. Anyway, reassessing the data and analysis used in the original study. That's what we do in the surprise paper. So first, comment on that study. So if you look at Gilovich, Vallone, and Tversky, we kind of gave an overview, but what kind of data did they look at? What was the shooting that was involved? They had one data set, which was field goal data. So what's field goal data? I think a lot of folks are familiar. Let's just set the stage. So this is live action, live ball data. So there's Steph Curry taking a wide open three, but it's not always going to be that way. Maybe he's doing well and they're going to want to crowd him, bump him, throw him off his rhythm, knock into him. Make him hear footsteps. So that's what it looks like. And so what do they find? They find that people shoot actually worse after hitting a few in a row. But if you start adding controls for these admitted variables, like this defense and shot location, the more controls you add, the less that negative goes away, and then it gets about 0 to positive. One of the issues with this data is that you can't put in all the control variables that you may want because not all of them are measured. Examples include maybe like the angle in which the defender is, say the quality of the defense, like does the defender occlude the view of the basketball player's view of the basket at the right moment. There's a lot of other things you could write down. Pretty much everything you omit is going to push it down in one direction. The reason why it was negative to begin with is because there's an incentive to adjust by the defense. If a player is hot, they want to make it more difficult for that player. And if it's more difficult for the player, that's why they're shooting worse. And if you control, everything you're missing out is probably something that's making it more difficult for the player. And nevertheless, of course, making it more difficult to the player may open up opportunities for their teammates. So Gilovich, Villen, and Tversky were well aware of this issue, so they looked at other data sets. One of the data sets is free throw data, so that's 2 shots taken successively from a fixed distance. And so this has some advantages in that you don't have the defense. It also has some advantages that you don't have to control for the shot location. It has some disadvantages because it's just one shot. So the issue of measurement error is particularly pronounced. And so one way of thinking about measurement error, you can imagine a basketball player, say, being sometimes a 40% shooter, sometimes a 60% shooter. If you take one draw from an urn that's 40%, say, hits, and one draw from an urn that's 60% hits, well, you don't know which urn it's from, let's say, 50-50. One draw is not a very strong signal of the urn's contents, right? And so there's a very good chance you can get a hit out of a 40% urn, a very good chance you get a miss out of 60% urn. And so this ends up essentially mixing together and you get this attenuation. And you might say, for example, get after a hit expected to get about 3% under kind of reasonable assumptions, depending on how you set it up. So that's the idea of measurement error. And measurement error is not restricted to field throw data. You can also get it in field goal data. One of the ways you can get it is the shots are often separated in time for a long time. So if you look at these data sets, you say the person has hit 3 in a row, maybe the previous hit was 10 minutes ago and the other one was 15 minutes ago. So there's a lot of issues in that kind of data. But they anticipated many of these issues and they had a controlled shooting design. And so the controlled shooting design has a few advantages, and there are some disadvantages as well, we'll discuss. So what does the study look like? They have 26 shooters. Each player is at a fixed distance determined where they thought they'd make about 50% of the shots. They're actually pretty good on average in guessing this. Each player moves in an arc, taking 100 shots. So one advantage is it eliminates strategic confounds, reduces measurement error. And the way it reduces measurement error is you have many shots, so you can actually condition on more shots than just the previous shot. But you still have the issue of measurement error. Okay, so any questions so far before I go on and discuss this test? No, okay, so somebody's microphone is on. I hear some kids in the background, but that's fine. It's not too loud. Okay, so let's take a look at what they do. You don't have to look at this table. This is just the table from their paper. We'll just kind of high level. They run 3 different identical tests, which is a runs test, autocorrelation test, and then comparing how well someone shoots after a miss versus a hit, which is the same thing as autocorrelation in a sense. But the main test, which is the test you see repeated in a lot of other papers, is how players do on a streak of hits versus on a streak of misses. And they find that they don't do that different. And so they essentially take each player, they calculate a field goal percentage after 3 hits, a field goal percentage after 3 misses. That ends up being a matched pair, and then they just do a matched pair t-test. So this is 1985, and different types of analysis you would see in papers then. Okay, so what does this test look like? How to think about it? So they're testing if the probability of hit given 3 hits is equal or different than the probability of hit given 3 misses. And so this is their t-test. So the assumption is that each shooter's sequence of shots is IID. And the shooting percentage, we're going to look at the shooting percentage after streaks of hits and misses. And so, for example, you could see a sequence like this, the hit, hit, miss, hit, all the way up to N. And how are we going to assign each of the shots to a category of after 3 hits versus after 3 misses? We're going to run through the sequence, and at each shot, at each T, we're going to look backwards 3 shots. And if the previous 3 shots are a hit or more, it's going to get put in one category. If 3 misses or more, it gets put in another category. And so naturally you'd think, well, it's random whether, if it's IID like a coin flip, whether the previous 3 shots are all hits or all misses. And so naturally you put it in 2 different buckets, the shots that follow streaks of hits and streaks of misses. And of course you throw out any streaks that don't fit in that category. And then you take this assumption that, okay, well, we're going to assume, approximately that these shooting percentages, hit after 3 misses is distributed normal, hit after 3 hits is normal, and then we're going to have the null that they have the same mean. There's no natural reason to assume the mean would be any different. So that's essentially the test. And so each player has 2 numbers, shooting percentage, in each situation. And so then we can check what we'd expect. So what do we expect in a test like this? So assume shot outcomes are determined by IID Bernoulli. So we know that those 2 probabilities are equal, right? So the probability of hit after 3 hits under our assumption is the same by definition as probability of hit after 3 misses, just because it's coin flips essentially. So we're going to simulate 100 shots from this data generating process, divide them into those 2 categories, and then take the difference. And so there's the shooting percentage after 3 misses, shooting percentage after 3 hits. We're going to take the difference. Intuitively, we should expect the difference to be 0. That's what GVT intuitively thought. Pretty much anyone I've ever asked, everyone I've ever asked actually, without knowing this, had guessed this. I would have guessed it too. Now, here's the simulation. So what are we going to do? We're going to run this 10,000 times. So 10,000 times, we're going to watch a player shoot 100 shots and calculate D, dividing this. And each time, we're going to put it in a bin, and we're going to look at the difference. And we might expect, on average, the difference to be 0, but sometimes it'll be positive, sometimes it'll be negative. And so let's run it. And so this should be going, but it went in Zoom, but it's not going here, and that's life. So let me see if I can get it to run off of here. There. Okay. I'm not sure if you guys can see that, but the simulation is running, and well, that was not what I expected. Anyway, the mean ends up being about 8 percentage points. Okay. So mental note, need a test also in teams. Okay, so that should be surprising. It didn't really have the suspense that I was going for. But you might ask, how does it depend on the length and of the number of shots, the length of the sequence, and the length of the streak that you look at? So the green line here is this minus 8 percentage points, and you can see that it gets quite big, the longer the streak you have. And so what this is telling you is you have a bias of about 8 percentage points, and that's quite large. That's nearly as large as the difference between, say, like a median and near top 3-point shooter. So that's enough, whereas if you have 0 difference, that's actually evidence of a hot hand, because if there were no hot hand, you should have negative 0.08, not 0. Okay, so why is there this bias? I'm not going to go through the explanation of the bias. You can look at there's a Journal of Economics Perspectives paper we have here that you can find online. There's also kind of maybe a simpler version. Well, they're both pretty simple. You could also just read the proof that's in the paper that is back a few slides. This is an online Momentum Isn't Magic. We have an explanation there. And then Kevin Ross has a Journal of Statistics and an online Shiny app that's also kind of nice and useful. Okay. Bias kind of speaks for itself. So in terms of, convincing anyone, there wasn't much convincing to be had because you can check it yourself. So Gelman wrote, a simulation to check it. You can check it with simulation. You don't have to prove it. There was also a check of what we had. This was commissioned by Daniel Kahneman. So Yosef Renaud and Maya Bar-Hillel validated it. And so then there was a Wall Street Journal article, and then there's David Stern reading the article and, enjoying it. Okay, so returning to the data. So how do we debias this test? Well, we take that 88 percentage points, and we find that bias is what we found, and we adjust the difference across players. And so here's what we find. These are 26 shooters, well, actually 25, because one shot so poorly they never hit 3 in a row. And this is the difference for all those players. The average difference actually is a little bit above 0. But once you adjust for the bias, it's about 13 percentage points, which is quite a huge difference. So when we do that, we have 5 players that are significant. And if you look at the binomial probability, what's the chance if you run 25 independent tests that 5 of them would be significant at a 5% level? That's highly significant. And of course, the effect size is quite large, 13 percentage points. But of course, it's a relatively large standard error, but still quite significant. So that's what you get in GBT. You can go further than this. Actually, can't really see the time here the way this is going up. James, do you have the time?
It is 2:50 or 1:50.
Good. Okay, thank you. Yeah, 20 minutes in. Okay, doing good. So this adjustment, you might ask a question. We're adjusting based on coin flips, but the underlying data generating process may not be coin flips. It could be some other model of hot hands. So we can look at a few. So we can look at different types of hot hands. These are just, these are not exhaustive, but you could think of positive feedback and regime shift. So positive feedback is this idea that you hit a few in a row and that causally impacts the next shot. But hitting a few shots may not be causal. You may just have some underlying evolving state, and then you just suddenly get in the zone or get in flow, and then your regime shifts and you're doing better. So hitting a few shots doesn't cause you to do better, doesn't cause you to have confidence. There might be a little of both. You could mix the two. So we just look at these 2 different forms. And so the first form, we're going to look over here on the right. We're going to be looking at the positive feedback first. And so positive feedback for hits is just you hit a few in a row, say 3 in a row, and then you get an increase relative to what the baseline probability is. And so we have a bunch of different models where the D is the increase is 0. So there's basically no hot hand. We're back to coin flips. And that's where there's a 10 percentage point increase, a 20, 30, 40. And so here we're measuring the bias, which is what we expect to get from this bias estimator and what the reality is. The reality is this D. And so the bias is pretty much the same regardless of the data generating process. So if you adjust by 8 percentage points, it's going to be about equal to the bias. So it's not off too much. Then if we do it for positive feedbacks for hits and misses, so now misses also have an effect. And so you're looking at the difference between hits and misses. It's also pretty close. And if anything, you're under adjusting. Now, regime shift, I'm burying a lot of stuff here. This is in the paper itself. We basically look at a model where you have a hidden Markov chain and somebody's hot about 15% of the time on average, but we kind of vary that percentage, but on average 15%. And then we look at the probability of getting a hit when you're hot and the probability of getting a hit when you're not hot. And so we're modeling these different probabilities. So here D equals 0 would be you always have the same probability. D equals 0.1 means when you're in the hot state, you're 10 percentage points higher than when you're not hot. D.2 is when you're in the hot state, you're 20 percentage points higher. But remember, we're not observing the hot state. We're only observing whether they hit 3 in a row. And so hitting 3 in a row is kind of a noisy signal of being in the hot state. And so this is what we would actually expect to see. It's a much bigger bias. And that's natural because this is basically all measurement error here because we're getting a proxy. So we'd be way underestimating hot hand. Let's say if the hot hand was 20 percentage points and we only adjusted for 8 percentage points, the remainder is essentially measurement error. So it would be conservative for a regime shift model. Okay, so what we've learned is the bias correction is conservative across at least these models, and also that binary data, at least if you look at this one, with the regime shift, it's weak and not really an ideal way to study hot hand, but it's all we got usually. Okay, so what's the contribution of this paper? Finding that the shooting percentage after recent success is the same after recent failure. That's evidence of the hot hand because of the bias, and that's the size of the bias. The evidence is meaningfully large in the original data set, and So the contribution is we have this counterintuitive statistical bias. Hot hand belief is not a cognitive illusion based on that test, and the effect is meaningfully large. And the paper itself encouraged more hot hand and momentum research. So that's kind of the baseline before we can move on. So what's the evolution of the field since this paper? That's a 2018 paper. So here's that old quote from Kahneman about the massive and widespread illusion. In May 14th, 2022, he was on a podcast where he was asked about the hot hand, and someone saying there's been so many studies. First they came out, say it did, then it doesn't. What's the current status? He says it exists. Amos Tversky made a mathematical mistake. It's absolutely crazy. Very hard to see the mistake even when people show you, but there was something else, and that's the failure of the entire field. And he goes on to talk about basically that they accepted the null hypothesis. And then Kahneman says, there's less of a hot hand than people think. It exists, definitely. It's significant, meaningful, like 7%. You'll see later maybe what he's looking at when he sees the 7%. 7% is nothing to sniff at. I mean, people make different decisions in terms of strategy in basketball based on 3 percentage point differences. So 7% is, and I think he meant percentage points. Okay.
Josh, just to interrupt you, Ian
Yep.
has his hand up with a question.
Sure.
I was just wondering before you go on, can you say why is there a bias? Because as you said, it doesn't feel like there should be. So I'm sure there is, but why? So why is probability of success conditional on 3 hits different than we would expect?
So there's different levels of explanation. I think the full explanation that would give a kind of an intuition that you could walk home with would take 10 minutes. Now at least I haven't found one. I can kind of give you a feel. So let me give you kind of a feel if you're just based on one. So let's say you're looking at the difference between the shooting percentage after a hit and after a miss. So with this one, that's basically let me just think. That's basically equivalent to autocorrelation. You can actually check the math. It's basically the same measure as first order autocorrelation. And so if you think about what is first order autocorrelation, you're multiplying the difference between what happened on this shot in the mean and what happened on the next shot in the mean. Well, you could choose at random one of those products, right? Because the autocorrelation is the product of this shot minus the mean times next shot minus the mean, summed together, right? Divided by, how many there are there. So you choose one at random. If I happen to be above the mean now, right, the next one is more likely to be below the mean because the mean is fixed, right? There's only so many shots. So it's kind of like I've taken one out of a sum, right? And the next one is likely to be less than the mean in order to for things to be on average equal to the mean. And so you could kind of think of it as a little bit of sampling without replacement. The problem is that doesn't explain everything. That it gives you the intuition for a strength of length 1, but it doesn't give you an intuition for a strength of length 2. So when you have streaks, it's longer. When you have streaks, it's a much stronger bias. And
so is this something that you thought about before interrogating the Tversky paper, or was it something that you were completely surprised by?
No, we were surprised. We stumbled into it. So So I can actually tell you a little. We're going to get to the 3-point study. We basically stumbled into it when we were analyzing the 3-point data that you'll see later. We used quickly. We had a different measure that wasn't vulnerable to the bias because we just did it from first principles. Then when we came across the data from the 3-point contest, our approach took a little while to set up, so it was much quicker to do their approach, which we could just basically plug it in and calculate. And it said there was no evidence of hot hand, but we'd watch the videos and we'd apply it to a player. I'm like, there's no way, it doesn't make any sense. This player would have come up with a much bigger estimate than what we saw would have been hot. There's something wrong. Then we ran to see what would their measure do to a coin flip, and then we calculated it, and it said heads were more likely after tails than after heads, and we knew that can't be true. And so then we knew we found something. You know, basically you have that eureka moment where you knew something that nobody else knows, right? You know, and so that's how we found it. And then was the task. Why is that? We have to figure it out. Got to do the math, because you know you have to kind of have an explanation for it. And so I think the best way to kind of convince yourself is that I think the thing I did, the thing I left out is I should have shown. There's actually a table in our paper where you can just lay it out for 3 sequences and just, you know, sequences of like 3 and just calculate it and see that it's true. It doesn't give you an explanation, but it convinces you that it has to be true. Whereas a simulation feels kind of like a black box. So I'm on a new computer, so I can't pull that one up. We might be able to get back to it though. Any other? James, you're muted.
I am, but Carl's got a question for you, so
Okay.
Go ahead.
Thanks, James. I was just going to say to Joshua that I'm a huge fan of this paper, and I'm going to try and teach it in 2 weeks' time. And I'm using exactly your 3 heads, the HT, just literally going through the 8 possible things that can happen, counting them. And that's about the best intuition I could think to teach it to undergraduates. But it's good. I have it on my computer here, so if you don't find it at some stage, I could, and you'd let me share it, I could show it. As somebody from a professional economist perspective, as opposed to teaching it to undergraduates, I think I could say some stuff that people might be familiar with, that it's a finite sample bias, right?
Yeah. I can definitely yes.
So it's akin to something that people will probably remember from time series. It's like you said, it's like measuring a correlation coefficient. So you run AR1 regressions. There's a bias in the AR1 regressions in finite samples, and for small samples it gets really big. So I know people don't really know the intuition so much for that either, right? But it's, you know, nickel effects and things like that. But people know it exists. So I think it's, your research studies, it's in this, it comes from the same universe as that.
It's definitely related to that. So if Ewell is from 1921 is the first one to have it, but that was in the context of autocorrelation. So Leo Hurwitz, who was a professor at Minnesota, was actually the one that first demonstrated it in the context of regression. So it's called the Hurwitz bias. So then later, I was like Neerlove and somebody else, Neerlove and somebody else did simulations demonstrating it in the context of regression, not when you're regressing on the last out, like the previous shot, but you're regressing on other variables that happened before that are correlated with the previous one. And they demonstrated that you have biases there. And then Nickel has basically a proof of that. But he wasn't the first to demonstrate, he just has a proof of it. But it's all related back to the Hurwitz bias. Now, this thing is definitely in the same kind of universe as that. Something really weird happens with these streaks and you're dealing with binary data where it gets super big in samples that you think go beyond the length that would matter, right? So like in the nickel bias, it's typically like 20 or 10 or, you know, lower than that. This is 100 and it still matters. Well, the reason why it matters is because you really slice the data down a lot when you take the 3. And there's something about these 3 shots where they're essentially, because they're overlapping with each other, right? So that really creates the bias. And so I think there's kind of a demand for an explanation here. So I can try to give a quick version of that. I mean, I'm not going to go to the 10-minute one, but you can just imagine that a researcher has collected all of these shots that follow 3 hits and like put them in a bucket. And so these are all the shots. You saw how they were assigned to the bucket. So we can go back to that red bucket. It's too bad I don't have the graph here because I actually have a full explanation of this visually, but I can give you kind of a sense of it now. So let's go back here to the red bucket. Oh, that must have been here. So in that red bucket, you're going to have a bunch of shots. And you can draw one of those shots at random and try to guess what it's going to be, right? And let's just say, for example, it's flip 42. Could be any flip, right? Well, if I told you X ante, we're going to look at flip 42, and these are just coin flips. the probability flip 42 is heads is 50%, right? Ex ante. But we didn't choose flip 42 that way. I know that a researcher stepped through the sequence, looking at each flip and deciding whether to put it in the bucket or not. So there's information for the whole sequence kind of embedded in that flip. And so I draw that flip at random. It's either going to be heads or tails. Let's say it's flip 42. I find that out. Now, there's two possible worlds. That flip 42 is either a heads or a tails. Now, you know how it was chosen. It was chosen because it was preceded by 3 heads. The flip itself could be heads or tails, though. Now, if the flip was tails, what would happen? It would interrupt that streak of 3 hits and prevent you from selecting flip 43, 44, and 45, because they couldn't possibly be preceded by 3 heads, because flip 42 is a tails. So it blocks flip 43, 44, and 45 for being preceded by 3 heads. So it reduces on average the number of flips that are in that bucket. Now, if there's fewer flips in that bucket, any given flip is more likely to be chosen. So the probability of choosing flip 42 is higher when flip 42 is the tails, because there's fewer flips in the bucket. So the likelihood of choosing what you just chose is higher in the world where it's 3 heads and a tails, right? Where flip 42 is a tails, because everything in there is preceded by 3 heads. So you're choosing between 2 worlds. Am I in the world where my current flip's a tails or a head? Well, in the world in which my current flip is a tails, that flip is way more likely to be chosen. So then that world becomes more likely ex post. So it's basically Bayesian updating. And so that's the essence of the explanation that we have that you can kind of read online. Unfortunately, I don't have the graph on that, but that's the best I can do probably right now. Okay. Any other questions? Okay. So got a mosquito in here. Summer down in Australia. Okay, let's go. So what about the hot hand phenomenon since 2018? Okay, so here's a sampling of recent empirical studies. So this is existence of hot hand and momentum in basketball. So I highlighted in blue kind of like against hot hand, red for hot hand, blue against. Looks like we only have the stuff for and everyone else is against, but that's not necessarily the case. It's just that's the first line. 3-point contest. There's 2, 1 in favor, 1 against. Live ball shooting. I'm very skeptical in general about our ability to do much with this live ball shooting. We've spoken to 2 NBA teams and stats people at NBA, looked at SportsView and Second Spectrum, this optical tracking data. It's very limited. Even that. So the stuff you can get online isn't even that, but even with that, like what you want is you want to get like a stronger measure of someone's current state. You know, you might want to track the trajectory of the ball to see like how they're shooting, but the problem is the optical tracking is so imprecise. The ball's all over the place. You can't really track the ball. You don't know exactly where the defender is. You can't see how well the defense is. Like, did they occlude where they shot, right before or not? And these things really matter. Like if you look at like Draymond Green or Shane Battier and those kind of players, I mean, they're very on top of, including or also just like roughing the player before, things like this, if you talk about Draymond Green, but other players do that as well. These things are kind of hard to measure, but they're costly, right? You risk fouls, you risk, you open things up for the other team. And there's this other one that's pretty funny. If you've ever watched Luke Cornett, look up Luke Cornett. He's like a 7-footer for the Celtics. So you can see how he tries to block shots, which is all about, he's not even close to the player. He just kind of jumps up in the air and gets his hands there. It's pretty funny. Anyway, team scoring. There's also evidence, I haven't assessed this one, evidence that there's momentum in team scoring. Momentum in other domains, you have stuff in arts, culture, and science, cricket, professional darts, professional archery. So that's, a sampling of what I could see out there. There's some other things out there. So I'll go through a few of these. So let's first look at the Ritzwaller and Romano. And so this is essentially a a criticism of our analysis of GBT. I don't know if it's a criticism of our analysis. It's more of a statement of the limits of that data set. I think that's a fair way to put it. In addition, what they do, we have this permutation test that's invulnerable to bias. They go further and prove some general properties of that test. So they have some theoretical advances as well. And so their basic claims they say is they establish that a substantially large data sets are required to derive an informative measurement of the deviation from randomness in basketball shooting. Now, that's not a new statement. There's tons of papers that have demonstrated that the original data set was underpowered for testing the hot hand at an individual level, which is what they're in essence talking about. And it's not super powered even testing it at a group level. Moreover, evidence against randomness in GBT experiment appears to be confined to shooter 109. So they say it's one shooter. And so it gives this kind of feel, if you read it, that it's all driven by an outlier. And some in the literature kind of read their paper that way. So here's Lantis and Neeson, who were just recently published in Journal of Sports Economics. They say, however, Witzweiler and Romano developed new tests. Applying their tests to Gilovich controlled shooting data, they find that the hot hand found by Miller and Sanjurjo is driven by only one shooter. Now, that's not correct. What Ritzweiler and Romano do is they have these kind of step-down procedures because you have this issue of multiple testing, right? So if you're testing if each shooter has the hot hand and you run 26 different tests, some of them are going to be hot just by chance, right? Because that's going to happen. And so you need to adjust for these multiple comparisons. And they have these kind of more efficient procedures than like Bonferroni, where they kind of step down. You first have this very strict criteria for the first shooter where you have alpha. You need a much smaller alpha, like alpha over 26 or something. And then you step down from there, and they find out that like really only one shooter is hot by this standard. But oh, wait a minute, one shooter is hot by that standard. So there's hot hand in that shooter. Two, if you throw out that shooter and you analyze everyone else, at least for the main measure, as a group, their estimate goes down by 3 percentage points, down to 10. You can see it actually here, down to 10.7 percentage points, and it's still significant. Now it gets a little noisier when you go to streaks of 4. I think that's what it is. Yeah. So this is streaks of 4 because that's 4 here. So that's without shooter. And then, if you look at it in other measures like fixed effects, estimates, it's also significant without, and I think a little bit more. So that's all there is there in terms of that statement. So these statements aren't giving you the whole picture. Okay, so let's go back, but nevertheless, we shouldn't get stuck just with GBT's data set because it's just one data set, and they're right. It's underpowered at the individual level, and it's not that well. It's moderately powered. I actually don't quite remember. I don't even want to make a statement on that, but the power is probably around like 0.5 and 0.6 or something like that. Okay, so cold shower for the hot hand fallacy. This is the paper that was accepted at Restat. You can it's not really a response to that, but it definitely speaks to that paper. And so we're looking at a bunch of controlled studies, and we're trying in one of the studies to increase the sample size so we can estimate the hot hand at an individual level. And so here's the task. There's a shooter that warms up. They always shoot from the same spot. It's calibrated, so they're expected to be 50%. They take 300 shots, and that sounds like a lot, but these players can do it. And they don't seem to do any worse than the last third than the first third, or the last 50, the first 50. There's no betting considerations for the shooter, unlike GBT. And they're paid on a random subset of shots. It's written in an envelope kind of next to them. They don't know what shots they're going to get paid for, so the hope is that they have an incentive to do as well as they can always. And this is what the task looks like. I'm not sure how well this video is streaming for you guys, but you can see there's a shooter, there's a rebounder, and the shooter keeps shooting. This is on their home court. I could keep going. I've actually chosen a video where they make a bunch in a row and then miss a bunch in a row. I'll just keep moving there. Okay, so we have two phases. So we have semi-professional male basketball players. It's one phase, and we try to check if it works out of sample. And we have extra sessions for a hot player. And then we survey the accuracy of hot hand beliefs. And so here's the overview of findings from that data set. So we have 8 players that have a lot of shots, and then we can pool all the players together that kind of came in ad hoc at the end. And we have some of that in the paper as well. So we have the first individual evidence of the hot hand. One player exhibits hot hand at 8 percentage points, and it predicts out of sample. So this player in phase 1 and phase 2 has this. Then overall, this is for all the players in our sample. It's 5 percentage points, so less than GVT. That's looking at 3 hits versus 3 misses. You may want to compare 3 hits to, say, not 3 hits, which would be like 2 hits, 1 hit, and anything else, including misses. And then, of course, as you would expect, it goes down, and it actually ends up, that couldn't be P. This must be a typo. The P.01, there's no way that's significant when my standard errors are 1.8. So this one's not significant. I think I made this today. So ignore that P less than 0.01. So if you look at that, it's not. Then we have Jagosinski et al. So this is data from Ohio State in the late 70s. And so we got a bunch of computer punch cards from Jagosinski, and he digitized them for us and sent us the data, which was awesome. And there were 2 individual hot hand that's kind of robust to multiple comparisons in that data. That's the average estimate when you look 3 hits versus 3 misses. But again, you only have 6 players. And then this one, if you look versus 2 hits and 1 hits, it's not different than 2 hit, 1 hit, and everything else. Here's GVT back with the 26 players. So that has the largest estimate so far. And it's still significant when you just compare it to 2 hits, 1 hits, and everything else. And then there's another data set. So Avugos et al., they have a replication of GVT. These are Israeli Olympians. So they ran a study. And we were able to, originally they were going to share the data, but then they lost it, but then they found like an old thesis. So we were able to reconstruct a table and get some tests out of it. And so we did find that the difference is significant, almost the same as GVT. And then it's also significant in that measure. So this is, relatively consistent. So the smallest estimate is pretty much in our study. The largest is in GVT and in Avugos et al. We have an individual hot hand in our study. So here's this player, RC. He hits 3 or more. His shooting percentage 3 or more versus any other shot. So that's hitting 2, hitting 1, or anything else. And then you can break it out and see how he does against all other categories. Hit 2 exactly, hit 1 exactly, missed 1, missed 2. And so he seems to be doing better in all of these. And players actually believe he is the hottest in games. So that's, an anecdotal thing. I think it's important to kind of emphasize this evidence for individual hot hand, because the entire literature is really about whether the hot hand exists, not whether everyone gets the hot hand. And so it may be that some players get do really well after a few in a row. Some players may get nervous after 3 in a row and do worse. Some players may have no difference. Maybe on the average, there's nothing. And so when you average everything together, you may not expect to see it. Who knows? You expect to see some players that have the hot hand, and that's all the belief amounts to in games anyway. And so setting it up so you have enough data to test one player is, I think, pretty much in spirit with how the literature began. There's actually a paper in the late 80s, early 90s, where Joseph Cadane at Carnegie Mellon, I think, had Vinnie the Microwave Johnson and thought he found the hot hand in his data, and then Tversky found an error in that. So that's kind of like a little old hot hand history. We also have a survey, and I'm going to just, because I can't see a clock in front of me, I'm going to ask James, what's the time right now?
It's 3:20.
3:20. And we're going to 4?
Yeah. I mean, you might leave a bit of time for discussion at the end.
Yeah.
But we've got to 4. Yeah.
Yeah. So this, this slide's been pretty tedious. So I'm going to slow down for the next slide. This is a survey. This is about beliefs. This is about essentially heterogeneity. And so we survey the shooters in our sample and have them rank the 8 other shooters who they did not observe shoot in our task, and to kind of guess who would have the biggest boost in their shooting percentage after hitting three or more, and order them. They didn't have to order all of them, but we encouraged them to order all of them. Not everyone ordered all of them. We also asked them to do a rating task where they rated them on a scale, I think, of 1 to 5 or 1 to 7. And then we also asked them to estimate the numerical difference. Now, the numerical estimate was very noisy and didn't correlate with the other two, but the ratings and rankings correlated, so we're focused on the rankings. We're not surprised that asking basketball players to give a numerical probability estimate, that it's noisy and doesn't correlate with much, because that's not something they're typically used to doing. So we look at the ranking. And so what are we looking at here? On the horizontal axis, we have the ranking of the players that were given by the judger, the person that was judging the other player. And we've looked at this where they include themselves and they don't, and it's robust. And so here, this particular judger number 8, the person they ranked first had the highest boost in their shooting percentage. It's above 0 among the other 3 that they ranked. The second person that they ranked had the 3rd highest shooting percentage among everyone else they ranked. The 3rd person had the 2nd highest, the 4th had the lowest. So that's doing pretty good. Now, this judger, the person they ranked the highest was not the highest among everyone they ranked, but it was 2nd highest. The person they ranked the 2nd lowest was actually the highest, but it's pretty darn remarkable through here. Next one, that one's perfect. That one's noise. I don't know if this person was cooperative. That one was pretty darn good. That one was really good. That one was really good. So that's almost too good to be true when I look at that. And it's highly significant. And so what I think is probably going on here, because it's just too good to be true, is they must be ranking them by how often players shoot. Some players are not good shooters, right? We have a mix of different positions. So we have centers, we have shooting guards, with these kind of things. And so some of the players just aren't that good shooters. If you're not shooting that often, you're not a great shooter, it's probably hard to sustain a streak. And so that's probably what's going on. We don't have, we can't definitively get to that because we don't have all of their in-season records to be able to answer that definitively. Okay. So summary, what do we find? These are the data sets. You can see, the number of people that are significant are more than you'd expect. And here's basically what you get if you look at this difference. So here's the difference between 3 hits and 3 misses. I don't report that. You can just see the individual for this other one, hit versus 3 hits and hit versus not 3 hits. And so, most of them are greater than 0. But the actual magnitudes you can see here, which we've already seen. And so that's kind of, you could think of as additional data beyond GBT, that it seems to be robust across settings. Any questions on that? Okay, so what about the 3-point contest? So 3-point contest is, this third paper we have. The reason why we chose it is because we're interested in pros and higher stakes and whether it kind of maintains there. And it also has this nice feature that they move around, kind of like GBT's study. We're not really sure how players moved around in GBT's study. They just said they kind of moved around in an arc, but we don't really know how they were assigned different positions. Here we can actually see. So what is a 3-point shooting contest? Here you see Steph Curry. He's shooting a basketball from Iraq. He always seems to choose the second ball, not the first ball. I guess it must be easier to grab. These first 4 balls are worth 1 point. The last ball is worth 2 points. And he moves around the arc, and he has a minute. And he gets very excited when he does well, right? So players are motivated to win this. So it has real motivated NBA players. In the first edition of Nudge, Richard Thaler wrote that without any defense or alternative shots, this would seem to be the ideal situation in which to observe the hot hand. Incidentally, this is not in the second edition of Nudge, which came out more recently. So this three-point shooting contest that he was referring to in the first edition, it comes from Kohler and Conley, who had this analysis of just 4 years of data. 4 years of data is underpowered. They also have the bias as well. So what we're going to do is we're going to look at this three-point contest in which they move around the arc through 5 racks, and we're going to improve on it. So we look at their analysis, we'll improve on that and get more data. So we collect all the data from 86 to 2020. So these are 33 players, each take, so we find 33 players that have 100 more shots. So there are many players that just have 25 shots, and a good number of them never hit 3 in a row or just have one observation of 3 in a row. So if you're doing kind of like a binomial test of like how many players are significant, if someone has 25 shots, they're never going to be significant, right? So you're basically, burning that. So if you just select based on players that have 100 more shots, then you're going to have kind of enough sample to do that. So we kind of set that as an arbitrary because that's what GBT had. All the tests kind of adjust for their shooting percentage anyway, and there's no reason to expect any kind of bias. And we might be over-selecting hot players. That's possible, but our question isn't whether we're getting the exact estimate of the average hot hand effect among players. We're just trying to find the hot hand. So trying to find hot players seems perfectly fine. And I would expect players that shoot better will probably more likely to have the hot hand. Now, what do we do here? And we'll look at the fewer shots too. So we'll do a robustness check of this at the end. So we're going to go on YouTube and watch a bunch of videos, collect the data. We're going to be going and collecting a bunch of DVDs that we get online, and then code up the data. And so if we do this, it's not obvious here, but if you do the test, 8 out of 33 are significant, which itself is quite significant. And the estimate among these players is they have an 8 percentage point difference when you compare 3 hits to 2 hits, 1 hit, and anything else. And it's highly significant. So adjusting for the bias, that's what we find. We go further. So we put this in a kind of different framework. So this is just a linear model with fixed effects, and we look at a bunch of different specifications. So this is a specification curve. So we estimate how hit depends on previous hit. So this is actually hit t-1. I don't know why it says hit t, but please think hit t-1 here. And we're going to look at the beta on the previous shot. And so that's basically estimating the difference between when you hit a few in a row. I think I just want to fix this real quick because it's annoying me so much to see it. No, I can't because I'm on a different computer. Never mind. So this is hit 3 in a row. I copied the wrong thing today. Please forgive me. So that's hit 3 in a row. That's the beta on basically how much better you do when you've hit 3 in a row versus any other situation. So we're looking at what this estimated beta is across a range of specifications. Now, the specification, some of the specifications are high, some of the specifications are low. You can kind of look here for patterns on what gives lower specifications. And so we're looking at what happens if, the original one with, at least 100 shots, we all go down to like every shooter, which is like 125 shooters, including many shooters that never hit 3 in a row. So that's a really kind of unbalanced panel there. This is a panel model. And we look at what happens when we drop the first 3 shots. And why would we drop the first 3 shots? Because there's a warm-up effect. And you see this in every study. So even in the other controlled studies, they tend to shoot worse in the first 3 shots. And so if you drop the first 3 shots, the estimate goes down because the comparison group now has a higher estimate than before because it doesn't have the first 3 shots in there. And so it brings it down quite a bit. But you can just kind of see the range there. And so you can kind of, make your own decision how much you buy this, but you can see for most of them, it's positive and significant. We control for session fixed effects, ball fixed effects, rack fixed effects, and you can check the paper there for more. Okay, so one natural question though is we've controlled for those effects, but what's the mechanism here? So is the mechanism that players are just they're in some state and they get hot and it carries over between racks? Is it that they hit a few in a row, it boosts their confidence, it's going to help them anywhere? Or is it that, they have some sort of calibration muscle memory thing going on within rack, right? Because it's very easy to repeat the same motion from the same position. Probably all of them are going on, and for sure calibration is going to be going on. And so we might want to try to rule that out. And so we do that in the paper, in the EER paper. We address it. I don't think the data is good enough to address it in a super convincing way, but it's there, so you can just, make up your own mind what you think. So first, it'd be good to look at how people shoot across different ball numbers. So here is here's how much. This is actually the time. So this gives you a sense of how people shoot differently. So they take more time to shoot the last shot in a rack relative to the first shots. So this is the difference in time. So they're always taking more time in the last shot. That's the money ball. It's worth more. And of course, they're taking way more time to take the first shot because they have to switch racks. And so those are the two kind of differences. The last shot and the first shot are different. And so we would expect to see differences in performance. So that's what we see. So here's the performance. You can see here's the first three shots. They, it looks like the first two more on this graph, but they build up here. They're doing better all the way through the first rack. But the second rack, they do better and then they drop at the end. The third rack, they do better and then drop at the end. The fourth rack, they do better and then kind of, I don't know, not obviously different, but drop at the end, do better, drop at the end. So they're clearly doing worse in the money ball and worse in the first shot. So they're focusing more on the money ball and doing worse. That's kind of an interesting finding itself. But we may want to know, is hitting the previous shots in the previous rack predicting whether they're going to increase, their shooting percentage on the next shot when they switch racks? Because it may just be some sort of calibration thing going on. So we're going to approach this, I don't think 100% convincingly. This is in our appendix, but it's something. We find data that's not inconsistent with that. It's an open question. So is this muscle memory or calibration? So what can we do? So this graph is a kind of simpler version of what you saw before. What we're doing now, the first row is telling you we basically cut out 80% of the data. We're just looking at one ball on the rack, basically. So like if we're looking at ball 2, we're looking at the second ball that they shoot on the rack for every rack. And so if they shoot 25 shots, you would be looking at 5 observations or if you drop the first 3, 4 observations. So we're going to focus in on the red highlighted area. That's the first ball in a rack. And so here is, the original specification. This is the first line. That's where we have 100 or more shots from each player. And there's the estimate, and it's kind of almost significant. And we've cut away 80% of the data. So this is super underpowered, but it still looks like it's significant. But then, as we vary the model, it drops a bit, not by a lot. So here, when we look at 75 shots or more, 100 shots or more. Now, we didn't include 1 shot or more because for the players that hit, only had 1 round, most of them didn't even have 3 in a row. So there's no observations. And when they have 2 rounds, there's a lot with no observations. But anyway, look at the standard errors and confidence intervals. We're not super well powered. So this is more just like looking at, are the estimates consistent with what you would expect? Yes, but is it powered enough to actually test whether it's different than 0? Not particularly, but at least it's consistent, and there's no strong evidence against that, mechanism of the carryover. Now, that's what we did in the paper. There was a 2021 kind of comment on our paper from Lantis and Nessen. It was covered in Marginal Revolution and some other areas, and they say, using data from the 86 to 2019 contests, we find a hot hand, but only within shot locations, which is contra to that. Our results suggest that any hot hand in basketball is only present in extremely similar situations and likely not in the run of play. In that paper, they do not indicate in the abstract or the intro that we tested for this in our paper. And I know this led a few folks, because I've spoken to them, to believe that we did not attempt to address the location issue, or were not aware of it because it wasn't clear. But we did, as you know. That's the old graph that you saw. Now, in the 2024 version, this is now acknowledged in the intro. So it's there, and they largely, aside from that particular question, for the rest of our findings, they approach it differently. They confirm it in a different way with a different approach. The paper was recently published, so there are no replication files. So I just put out a request to kind of check them out, but I haven't heard back yet. But I'll go through it at some point this year. But in any event, it does confirm our findings. But they do go further. They look at other patterns besides streaks, like let's say you have a hit, and a miss versus 3 misses. And you would think that having 2 hits would increase the chance, right? If even though you missed it, and they don't find a difference. I guess the thing I would caution is that we're really thinning out the data when we start looking at more different patterns, especially if we're focused in on the carryover onto the first shot of the next rack. So there's essentially mixed findings. So they find findings that are inconsistent with that. I don't think there's really a way to reconcile, because the power is so low that depending on how you approach the analysis, and they approach it in a different way, and what you control for, you might find different findings. And it's, yeah, I think you'll see. So we approach it in a different way. I'll show you kind of an example of this. So let's take another kind of underpowered look at location. And so this is back to where we were. So we're looking at the first shot, and these are all highlighting the first shots. We're going to zoom in on those. And so this is just the first shot from the rack. And here we are. And so here's the first shot from the rack, zoomed in. 3 means we're keeping only shots 4 through 25, and 0 we're keeping 1 through 25. And so of course the estimates are a bit higher when you keep the first 3 shots, and they're a bit lower when you don't. And we have the min 75 here. And so one of the observations that Lantis and Nessen made was that we didn't include players that had 1 round and 2 rounds. Now here's just a fact: 47 out of 71 shooters with 50 shots or fewer have no observations of 3 hits before the first shot. So they're not really adding anything to the analysis. You're just putting it into the unbalanced panel. So make that what you wish, but we can throw it in. So here we throw it in, and it does bring the estimate down when we throw it in. And so that's one of the observations that's made in the paper. And let's zoom in on only the shots where you don't have the first 3 shots. We're only keeping the shots 4, 5, 6 up to 25. So we're not getting any action out of those first 3 shots. And then let's expand to streaks. So we're looking at conditioning on hitting 3. We compare conditioning on hitting 2, hitting 1, hitting 4, and it's ordered. So what you see is if you have 4 hits in a row, you get on the previous rack, right? Because we're only looking at the first ball of each rack. You have 4 hits in a row. You're going to be doing better than 3 hits in a row, then 2 hits in a row, and then 1. But 1 is negative, so that's a little weird. Like, why would you do worse after hitting the first shot, of the previous? So you can kind of see how noisy they are. You see how big the standard errors are. It's, kind of consistent with it, at least it increases. But that's just another way to slice the data that's consistent with it. There's other ways you can look at it that will be inconsistent. It's pretty noisy. And so that's kind of all I have to say about that. I'll take a pause before. Any questions at this point? Okay. So is there any way to get evidence about location not being the driver of this, right? So the strong conclusion of Lantis and Nesson is that it's all about location and they just do well at a fixed location, but it's not going to carry over between. Is there any other way of getting at that question? So I hope I've argued that we haven't answered it, but it's not clear that the opposite is true either. It's just kind of a little bit ambiguous. It's kind of consistent with it, but not overwhelming. I think this is the best location independent evidence, and I'm about to show you. So Craig Hodges had a 54% field goal percentage with nearly 500 shots across contests. He had the most shots. They invited him back even when he wasn't in the NBA. That's how good he was at this. He never missed more than 5 shots in a row across the entire contest. And he's a 50% shooter, so that's pretty remarkable. And then there was this, and I think this is worth watching. I don't know if the sound is coming through, but this is going to be a minute, and I think it's worth watching.
There's no sound, but we can see it moving, Josh.
That's 5 in a row. That's 10 in a row. $18, $19. He missed. And we'll stop it from there. So you can calculate what's the probability of a 54% shooter who shoots 500 shots in the number of rounds that he did with those length. What's the chance that that happens? He gets 19 or more. So that's approximately how big it is, right? I just did the calculation for 50%, but I've actually done the calculation for 54. You can just plug this into a formula to get this one. So that's quite small. Now, of course, he's one of 120 players, so you got this multiple testing issue, but you can adjust for that. And you have to remember that not everyone had 500 shots. A lot of people had 25 shots. A lot of people had 50, 100. So this is, given the data that we have, we can do this adjustment for multiple testing, and it's still significant. It's less than 0.01. So that's probably the strongest evidence of carryover between racks. Now, it's not evidence necessarily of the confidence mechanism, positive feedback, right? Where a player hits a few in a row, they get confident, they're more likely to make the next shot. We don't have necessarily, it doesn't look like evidence of that. It looks like he just showed up and was better that day. He was hot that day. So it's some sort of kind of state-dependent hot hand rather than a positive feedback type hot hand. Incidentally, there's Gary Smith has a blog where he actually does this calculation, but he overstates how significant it is. It's not that significant, so don't take that. You can actually calculate it. You can do the permutation test, or you can just kind of do a back of the envelope. So he's off by an order of magnitude, but it's still significant at the 1% level. So it's a thing. Okay, James, how are we doing on time?
It's probably worth you wrapping up if you want any time for questions, Josh.
What time is it?
It's about 3:45.
3:45. Okay, so I'm going to wrap it up. So I think at this point we should be a little, have a little humility when we think about practitioners and what they believe, because the original GBT paper was about showing how dumb players and coaches are. So I encourage you to watch this video of Steph Curry being interviewed on this first week feast. I have the kind of link here. It's just from the 5-minute mark to about the 7-minute mark. So he's asked about Gilovich, Malone, and Tversky's paper and about the hot hand. And here's what he says. There's times when you catch the ball and maybe you made 1 or 2, and this is in practice or a game, and whatever's the case, mostly in a game, everything else does not exist. So he's kind of talking about the zone that he gets into. And as long as I get the shot off and it's not going to get blocked, the rim feels like the ocean. It's the most rewarding feeling. And, that's all the work. That's all you work for, this muscle memory, the mechanics. It develops the confidence. And then when asked about their study, he just basically says, they don't know what they're talking about unless you've been in that 94 feet. So that's the attitude. So also these players aren't really listening, right? And maybe they don't need to. This doesn't necessarily mean they're making great decisions, though. So there's an example from 2016 of players kind of getting too excited about the hot hand and getting out of their game, and they're the coach or other players saying it's not their style. They get too excited about giving someone the hot hand. And just actually this week, so this is from January 23rd. This is Cat, Karl Anthony Towns. They got excited giving the hot hand, and the coach kind of scolded them for playing immature basketball. So there's the coach. I mean, there's lots of times when just because you've scored 2 or 3 or 4 points in a row or baskets in a row, obviously we're going to try to feed a hot hand, look for a hot hand. But at some point, we got to get back to making the right play. We got to get back to doing the right things. So this is not to say that everyone's walking around making great decisions here. And so my provisional view, this hot hand debate relating to in-game shooting, it's going to go on for some time. I don't think it's that productive because of measurement issues, unless there's some advancements beyond what we have. I don't think it's going to be definitive. It's going to be mixed. It's not generally relevant to momentum in other economic settings like personnel, labor, because it's, the existence of the hot hand itself is so domain and specific to the task. We might be more interested in kind of beliefs. Of course, it is interesting if we think people get hot at work and things like that. That might be interesting. I haven't seen much of that, but you saw some of those other papers earlier. I think more promising avenues is looking for domain-independent mechanisms behind momentum, like confidence, belief updating, motivation. And so there's a recent CLII paper by Deschamps and Lionel Page that's, I think, interesting to check out. And so just to summarize, I'll just leave this up here, what I think our contributions are in terms of what we have here. So, the original overlooking a counterintuitive statistical error. Then there's the psychological behavioral contribution that it's not a cognitive illusion, that the belief in a sizable hot hand is justified at least. Beliefs can be profitable. You haven't seen the prediction stuff. We have a paper on that, hopefully to submit soon. People do predict well. Players appear to know each other's hot hand tendencies. That was that survey. And then there's the scientific contribution of correcting the record and saying researchers have been too quick to dismiss practitioner beliefs. And so momentum kind of has been under-investigated, more generally. Now, I'll just thank you. Thank you, everyone, for being here. And, I've been staring at a blank screen. I don't know how this has landed on your end. And I know it's 2:30 in the morning here, 3 in the morning here. I don't even know what time it is here. Anyway.
Thank you very much, Josh, for such a coherent speech and talk for such an early in the morning hour for you. So thank you very much. It was very coherent. It was very interesting, even to a non-basketball person like myself. Ian's got his hand up first, so I'm going to pass over to Ian.
Joshua, that was great. I played basketball this morning, so I was trying to think about how I was feeling. And it really does. It feels like a feeling. about how easy the game is. I know everything you showed us was about the probability of making the shot.
Yeah.
But when I'm missing, I'm sure I'm exerting more effort. So I'm kind of adjusting my effort as I'm being hot or not hot. When I'm in the zone, everything feels easy. And so my effort is somewhat reduced. There's no adjustments to make. If I've just missed, I know I have to make an adjustment. That's like cognitively difficult for me. But if I'm in the zone, if I've hit, there's nothing to do. I've just got to do what I did before.
Yeah.
So it doesn't really feel, well, I don't know whether the probabilities will be different for me, whether I've just missed or whether I've just hit, but the feeling inside is very different. Like that is something definitely unambiguously there. So I don't know if people have tried to measure the sensation of hot hand, or if they've tried to measure effort exertion in a different way rather than just the probability of success as the dependent variable.
So I haven't come across a measure of effort exertion. It makes sense as a, as a mechanism. Like if you listen to Steph Curry's interview, I mean, that's essentially part of the mechanism he describes, which is, he doesn't necessarily talk about hitting 2 shots in a row makes him a better shooter. He thinks 2 shots in a row kind of confirms the kind of feeling that he has and gives him the confidence to continue relying on his muscle memory and motor mechanics, basically being unconscious about shooting. And so he's eventually saying the same thing you're saying on some level, right? Which
that is
not
the only way in which me and Steph Curry are alike in our shooting.
Yeah.
In no other respect have we get close.
Great. Thanks, Ian. Many more questions and comments? Stefan, then no. Oh, Stefan had his hand up, then it went. Stefan, as a sponsor, I feel I should go to you first.
I get preferential treatment. Absolutely, very good. Thank you, Josh. It's amazing, and I think your work is incredible, and I'm just a huge admirer. And I remember when you first saw your working paper come out, I thought, "Whoa, that's really." I got to change the way I think about things, and that was just a really great moment when somebody proved something to you that you had convinced yourself wasn't true. So thank you for that. But I was just wondering whether, in terms of thinking about sequences and whether there's anything in whether particular sequences which are consecutive rather than have this phenomenon of persistence, if you will, whether you could compare this with another sequence which is not consecutive. So if you compared, say, for example, the success in free throws, because free throws, you're taking them, there's lots of things going on between sequences of free throws that you've taken. And presumably there you would expect not to see a hot hand. So that would be pretty clear. And that's a clean test as well, because it's just you and the basket, and you can see that. So you could compare whether there's a hot hand in sequences that are consecutive as opposed to sequences that aren't consecutive.
Yeah, I would expect free throw. Free throw is a strong calibration component. I mean, first they're already shooting like 80%, so hitting a shot is not not that much information about their current state. Yeah, I wouldn't expect it to carry over if someone has a free throw, 5 minutes ago, 10 minutes ago, and they hit one shot, for that to be that predictive over a long sequence. I'm not sure what it would show to show that it doesn't. I mean, I guess it's useful to do because I don't think anyone has, I've seen quite a few free throw stuffs. I've analyzed it myself, kind of confirmed that, you're more likely to hit the second shot after making the first shot. Never checked, what if, I don't know how often, how many free throws the average player takes a game. But you can go and check that. I wouldn't expect there to be a difference. Now, what do you think that would show to not see a difference?
Well, I don't know. My intuition was that this is about sequences of shots, and people and players take sequences of free throws. So we can list the number of free throws they've taken, and that forms a sequence. It's just that they're not. There's gaps of action in between them. So in some sense,
yeah,
it's similar to sequences of shots, but without. But the difference is that there are gaps in between, and so that if there's a hot hand, you would. That's essentially a claim that some sequences without gaps have some extra characteristic which sequences with gaps don't have.
Yeah. Right. So yeah, I think it would be interesting to check. I'm not 100% clear how that would change my views on hot hand if you found that there was no difference between them. My sense is that you would have an issue with power, but I haven't done the simulations. So because we have to remember that I don't know what the typical player's free throw percentage is. It must be like 70%. And if they're taking maybe a couple pairs a game, like you kind of have to sit down and like simulate what we would expect for different types of hot hand, and what do people think of hot hand? Do they think of hot hand as lasting an entire game, or do they think of hot hand as lasting 10 minutes? And so, I mean, I guess it could rule out this idea that someone shows up and has hot for an entire game. Because if you go and do this analysis and you find that there's, no difference, and it's powered well enough according to your simulations, then you can say, okay, well, this idea that someone's hot for a whole game is not really reasonable. And this is like one of the criticisms of, like one of the examples I gave, I think it was of the Karl Anthony Towns one, where he was shooting really well in the first few quarters or something, and then they just started feeding him, and at the end he wasn't shooting as well. And so, yeah, so if it's an ephemeral thing, then you could rule out that. Yeah, no, I mean, I think it's worth thinking about further. I'm trying to get my mind around it on its relevance, and that's probably all I can find at the moment.
Well, could well be irrelevant, but thank you anyway. Thanks a lot.
Yeah.
Thanks, Stefan. We've got only a couple of minutes left. We've got a couple of questions. So Carl and Danielle, and if you can keep them relatively short, that'll be great. Thanks.
Yeah, just two quick observations. They don't need to be answered, but one is whether or not you have looked at real-time sports betting markets in terms of basically the Bayesian updating that they're doing in terms of real-time bets on how many points somebody's going to score in a game, and where that money goes. We know a lot of bettors believe in
That's
momentum.
cool. Yeah.
I'm thinking
I haven't looked at that.
James and co-authors have papers about when a soccer team scores a goal, people perceive there to be a momentum shift that, if I understand it correctly, James, isn't actually there. But there's quite a lot of money going in real time in these markets now. Where you get these data, I think it's perhaps need to co-author with or partner up with a provider, but there's a lot of money being spent on real time betting, and we can see as the guys shoot the baskets and seem to get the hot hand what the bookmakers are doing. That would seem like one way to get at these issues. And the other was just in relation to that team that lost despite the 62-point guy. Is it possible to calibrate, how much a hot hand ceteris paribus should help a team win, and then do they actually win that much more? Can we see an offsetting effect coming from their adjusting and going away from their normal strategy? Again, obviously, ceteris paribus, one of your shooters gets hot, should help you win. But if you change your whole plan to feed him, maybe you're not as efficient, maybe you become more predictable. So that know if that's designable, but you provoked the question by putting the slide up about the guy who got 62 points. So anyway, look, great work. I'm a huge fan.
Thank you. Yeah, so just, I don't know if we have time. I can just quickly address the Kammerer had that original betting market paper, and then Brown and Sauer replied, and they, you know, there was momentum in team performance, and that's been replicated. There was a certain degree of overreaction to that momentum in betting markets, but not enough to be profitable, you know, within the bounds. And I think that generally happens. You know, there's so many people out there that are just applying models to these betting markets. But I would guess in the real time, it's harder to kind of set up these models, so it's less likely that, you know, these discrepancies will get arbitraged out, and you're more likely to find people overreacting if it exists. So I think it's like a promising area. And then on the other one, I don't know too much about, you know, the value of the hot hand. I know we've spoken to an NBA team, and they were uncertain how to respond, whether, you know, because they tend early in the game when it doesn't matter as much and a player's shooting well, they'll basically ask, you know, they won't give any extra help, or they won't blitz, or they won't give another player. They'll just say, like, play the person a lot harder, right? You know, bump them, knock them, these, you know. So that's still costly because you're risking a foul, right? And that could happen. So they're willing to risk that much, but it's not till later in the end of the game that they're willing to give up even more, like, you know, switch somebody on and things like this. And they wanted to figure out, like, when can they, you know, are they making the right decision, right? And it's actually really hard. So we didn't have an answer really, but yeah.
Great, thanks, Carl. Thanks, Josh. Quickly from Daniele.
Yeah, so super interesting research agenda, and you know, really striking results in the original paper, and then all the follow-ups. I guess there's one point that I'm still, you know, not completely. I'm not sure I understand what the main takeaway is. So is it that, you know, all players actually have a probability, you know, the probability of hitting shots is not serially independent, you know, so the probability of hitting shot t+1 depends on the probability of hitting shot t? Or is it that all players have some probability of sort of switching regimes? So some of the time they hit shots independently, and then with some probability they get hot. And so, you know, there is serial dependence in the probability of hitting shots. And, you know, the third option is that it's just some players that have this, or maybe some players, you know, you understand what I'm trying to say? You know, is it, you know, is it some players some of the time, some players all of the time, all players some of the time, some other combination?
Yeah, so it's some players some of the time, would be the answer. Now, the mechanism is, you know, that you propose, whether it's, you know, positive feedback, you get confident you do better, or whether it's some regime shifting state. In the data we have, they're observationally equivalent. Because basically there's no, you know, it's just time, right? So the future is going to predict the past as well, right? You hit the next 3 shots, you're more likely to hit the current shot in this data, right? But of course, the future can't affect the present. And the problem is this is just like, you know, ordered data. We don't have a way of just randomly assign someone, you know, to hit a few in a row, miss a few in a row. And so it's possible that they're just, you know, they get in the zone and they do well for a period of time and then get out of it. It could be that there's some positive feedback. Could be both. We don't really have an answer to that. To answer the question whether, like, how do we know it's some of the players? Like, what's the evidence of that? Well, you know, there's more evidence for hot hand than cold hand, because we can look at, like, comparing hits to everything else versus misses to everything else, but there is some evidence of cold hand. Then you see a distribution, you know, that's not consistent with everyone having the same effect. And then I think the probably strongest evidence that there's heterogeneity is the survey that we have. And that's probably the strongest evidence, because then it predicts. And you would expect that, right? Because people that don't shoot that often probably aren't going to be able to sustain a streak and rely, you know, if the mechanism is, like, as Steph Curry said, is, you know, you have this kind of muscle memory thing, and when and when you're confident in your shot, you just keep repeating what you're doing because it's working. Well, somebody that's going to have confidence in their mechanics is somebody who shoots a lot. Is going to be a high volume shooter more likely, and a low volume probably not. And so you would expect heterogeneity just based on that.
Thank you.
Yep.
Great. Thanks very much. Sorry to Jean-Louis, who put his hand up a little bit too late. We're going to have to wrap up because we've gone past our time, but we've gone past our time because it's been fascinating content. Thank you very much, Josh, and thank you for being up at 3 a.m. Your time. I wish you a very sound night's sleep now once we're finished here. And thanks everyone. We'll be back again next week. And next week we have Ray Fair of Yale University presenting physical decline rates, men versus women. So have a great weekend and look forward to seeing you all again next week. Thanks
Thank you,
everyone.
everyone.
Bye-bye. Cheers, Josh.
Cheers.